Thank you very much. So let me start by thanking the organizers for the kind invitation. It's my pleasure to be here in the Silicon Valley of Berlin. Today I would like to talk about three-point functions and form factors and the string field theory vertex. So in this problem, you can see here, we are interested in an amplitude in which we take a big string. This is going to be a type 2b string on this ADS5 cross S5 background. And then if you impose some light cone gauge fixing, then it's going to be a two-dimensional integrable quantum field theory, which has particle-like excitations. So these are the trajectories of these particles. And this big string is going to split into two smaller strings, and we would like to calculate the amplitude in which you specify some incoming multiparticle state and two outgoing multiparticle states, and you would like to calculate this amplitude. So just to remind you that this problem has three sides. On one side, you have this string theory at strong coupling. You have at weak coupling, the n equals 4 super Young-Mills, and they are related via integrability. And the observable I would like to calculate today is this string field theory vertex, which is related to the three-point functions, and I will show you that it's related to form factors in the integrable language. So this work is done in collaboration with Romuald Janik mostly, and some part with Andrzej Vereszyński, and these are the papers, relevant papers. So let's just recall these three sides of the problem. So typically you have two couplings because we are working in the large n limit. So you have the gauge coupling or Toft coupling on one side, and then once you calculate two-point functions or three-point functions of operators, then you have the size of this operator. And then gauge theory is reliable and a good calculational tool for small couplings. This is perturbative gauge theory. And then you start to calculate loop corrections, and then you have this strongly coupled gauge theory. On the other side, if you go to very large gauge couplings, then you have classical string theory. Here, the inverse of the Toft coupling is the Planck constant. So when you calculate quantum corrections, it's an expansion in 1 over g. So, and then you have to sum up all these corrections to get the quantum theory of strings. And this holographic conjecture states that these two things are actually the same, the quantum string theory and the strongly coupled gauge theory. But of course, you cannot really relate them because the reliable domains when you can do calculations here and here doesn't really overlap. So the way you can show integrability, we can show this equivalence is integrability. So integrability operates quite differently. So first, you go to infinite volume or size, and you calculate the relevant infrared quantities in infinite volume. These are like the scattering matrices or masses. And then you systematically take into account the finite size corrections, like the leading corrections are polynomial in the inverse of the volume, and these are momentum quantization. Or if you go to exponentially small correction, they are due to these virtual particles. So if you sum up all this finite size correction in the ideal case, then you will have an exact solution. And then you can expand your exact solution for small or large coupling. And then you will see that it matches with the perturbative calculations on the two sides. So let's see how it goes for the first observable. So I would like to recall this success story, how we calculated the two-point functions or the spectral problem. So it's the similar picture, just the observables are shown. So here at small coupling, you have just spin chain energies. And then loop corrections, you will have not a nearest neighbor, but longest interacting spin chains, and you have the scaling dimensions, and the scaling dimensions of the gauge theory are related to the energies of the quantum strings. In the integrable description, you are interested in the finite size energy spectrum of a 2D integrable quantum field theory. in a finite volume. So first you go to infinite volume, you calculate the S matrix and masses, and then you take into account the finite size correction, and then very nicely you can sum those up, and you will have like a thermodynamic beta ansatz or a quantum spectral curve. We heard a nice talk yesterday about the quantum spectral curve, so it appears exactly in this way. So let me explain actually how we arrive this type of solution, gaining intuition from integrable two-dimensional models. So let me just... So I'm talking about this part now. So let's take the simplest interacting quantum field theory in 1 + 1 dimensions. This is a quantum field theory of a single scalar field with this cosine hyperbolic interaction. And interesting observables in this theory are the finite size spectrum. So in a finite volume, you put some particles and you are interested in the energy of this system, or you are interested in the correlation function. Here I just indicated the 2-point function in the cylinder. So this is an operator insertion here, there is another one here, and then by putting a multi-particle states in between, you would like to calculate this 2-point function. So here you are interested in the matrix element of this local operator between the vacuum and some finite volume state. So these are the quantities we would like to calculate in finite volume, but these quantities are extremely difficult. So the way we do is to go to infinite volume. So what we do, for example, if we analyze this process in which we have just two particles, in finite volume, these two particles would scatter and scatter on each other infinitely. But if you cut your cylinder and instead you analyze this infinite plane, then it's just one single scattering. And then as a starting point, you would like to calculate the scattering matrix. So why you can do it? Because there is this in infinite volume, you have this beautiful Lehmann-Simancic-Zimmermann reduction formula. And this reduction formula tells you that if you would like to calculate the matrix element of an operator between like a two-particle state, then you can use actually the correlation function, what you can calculate perturbatively, and you just act with some integral differential operator on the correlation function. The physical meaning of these integral differential operators are that they amputate the 4-point function in this case and puts the legs on shell. So the S matrix, if this operator is just 1, this is the S matrix. The S matrix is nothing but the on-shell value, amputed on-shell value of the 4-point function in momentum space. So what is nice about 1 + 1 dimensional theory is that if you take this Lagrangian and then you normal order the terms, then perturbation theory is completely well-defined. There are no infinities. And even if you calculate this S matrix following this prescription, then you will see that it's convergent. It has a finite radius of convergence. And then it's not an easy calculation, but you can go actually up to 4 loops, and then you can calculate this result. The result is written in terms of these rapidity differences of the particles. So it's 1 + 1 dimension. It's advantageous actually to trade the momentum to the rapidity, because we learned from Alessandro that the boost acts like shift in this rapidity, so relativistically invariant S matrix depend on the differences of this boost. So this is what you can learn from this 1 + 1 quantum field theory. You can do this calculation perturbatively and you will have this result. But what you can learn more is that taking this expression, this defines the S matrix for any loop order. So you can just collect all the information, all loop information in this perturbation theory, and then you will see that S matrix satisfies crossing symmetry. This is just exchanging one outgoing antiparticle with an incoming particle. Then the S matrix should be the same because they are analytically connected. So S matrix should satisfy crossing symmetry and unitarity. And actually, that's the way how bootstrap operates. So you take some theory, you do perturbation theory to all orders, and you extract information which is valid for the exact S matrix, and then you formulate these axioms which the S matrix should satisfy and try to solve it. So how does it go? So for example, if you had more particles, then the free particle going to free particle decompactified process will factorize into two particle scatterings in two different ways. Actually, this provides the Young-Baxter equation. But in this Sinch-Gordon theory, we have just one single particle. So the scattering matrix is one function which satisfies this functional equation. And then assuming that the asymptotics is just one, then you can find the simplest non-trivial solution. And the simplest non-trivial solution of this S matrix is written here. And then what you do, you expand in this parameter A, and then you compare it with the perturbative expansion. And what you will see that if A is actually the sign of this guy, what is on the right-hand side, then you will exactly get back the perturbative S matrix. So this bootstrap solution solved for you the Sinch-Gordon theory in a very easy way. Once you have the S matrix in infinite volume, you can easily calculate the leading finite size correction of the energy levels. So let's assume we take a finite size and we put n particles in a finite volume, and we would like to calculate the leading correction and finite size correction, which is polynomial in the inverse of the volume. And then this is nothing, just the momentum quantization or the periodicity of the wave function. So what does it mean? If you take one particle and then if you move around the circle, then you should pick up this translational phase e to the IP1L. But since there are other particles, they will scatter on them, and then you also pick up the phases of these S matrices. So this whole product should be 1, and this is so-called beta-Young equation for the rapidities, what you solve. Once you solve, you plug back to the energy formula, and you have an almost exact energy expression for large volumes. So this is the bootstrap program, how it works. And this was implemented. Here you see, not here, here for the two-point function. And now what we would like to do actually now, we would like to repeat something similar for the three-point function. So the observable is say, a perturbative three-point function, which can be mapped to some spin chain partition function at weak coupling. As strong coupling, we have this surface in which the big string splits into two small ones. The question, what is the integrable formulation of this problem? Because if we could figure out what is the integrable formulation, then we can easily use bootstrap to calculate this quantity. And then, first we should recall what is the form factor bootstrap in relativistic theories. So it was formulated by Smirnov and Karofsky. And then let's assume you are again in infinite volume and you would like to calculate a two-point function, two local operators inserted at the origin at maybe some imaginary shifted time. So the way you calculate this two-point function is that you insert a complete system of multi-particle states. In integrable theory, these are just the asymptotic states whose S matrix we already calculated. So you insert this state, and you would like to calculate the matrix element of a local operator between the vacuum and this multi-particle state. And the idea, again, is to formulate axioms or a restrictive functional relation which this quantity satisfies. And the equation, let me just depict this this quantity, like the operator is inserted here, and then you have incoming particles, ordered particles in this phase. So this is a kind of initial state. And then you can, again, in infinite volume, you can use crossing symmetry. So you can cross this guy up and back again, and it should be the same process. So this form factor, what is written here, it should satisfy this so-called periodicity property. And alternatively, you can just shift the trajectory a bit, and then such that these two particles meet before reaching the operator. So this means if you exchange the order in the form factor of these two guys, then you pick up the S matrix. So these are the functional equations I'm supposed to solve, and then I will have the form factor. But of course, you need to know the analytic structure. And you know that poles corresponds to bond state typically, but there are theories where there are no bond state, but still there are poles which exist for any form factors. And then these are the kinematical poles. And they happen exactly when one incoming particle and then one outgoing particle is exactly the same. But since we are analyzing form factors where all particles are incoming, so if we just take this same rapidity outgoing particle, cross it back, so if these two guys, the rapidities differ by I pi, then you should have some singularity. Actually, this is a very similar factorizing singularity we had yesterday in Amit's talk. So then you can calculate the residue, and the residue is proportional to a form factor which has two particles less. And then there are these two terms here. So if they just meet without reaching this operator and the other particles, so this is one. And then there is another contribution you are supposed to subtract when they go around and then scatters on all other particles, and there is this prefactor 1 minus product of the S matrices. So once you know this S matrix, then you can formulate recursive equations for the form factors. You start with the two-particle form factor. For example, in the Sinch-Gordon theory, the general solution of the two-particle form factor equation, you just take these equations, you specify for two particles, and then you introduce this shift operator, and you will see that if you take the logarithm of this quantity, then you have to just invert the shift operator acting on the logarithm of the S matrix. So this is a nice form. You can make it slightly more precise. So this is a two-particle form factor, and then using this relation, you can recursively build up any higher particle form factors. So once you know the infinite volume form factors, the message for the finite volume, large finite volume form factors, that it's exactly the same. Just you have to modify this expression with the norm of the finite volume states. But basically, they are the same. So this is the form factor program. It's successful. It has been completed for Sinch-Gordon and many other theories. Now we should somehow transport these ideas to calculate the three-point function. And this is the outline of the rest of my talk. I already explained this motivation of the S matrix and the form factor bootstrap. And now I would like to apply this form factor bootstrap to calculate the three-point function or this string field theory vertex. I told you that what was crucial was the crossing symmetry. So I need to decompactify this process. And actually, I can decompactify two different ways. And I will explain these axioms. But they are very, very complicated axioms, not that easy to solve. So I will make one more step. So I will introduce one more cut, send this other volume, say, to infinity. And I will introduce the octagon amplitude, what I will call the octagon amplitude. And then just to make connection with this nice work of Basso Komatsu Vieira, I will introduce one more cut to get two hexagons. And I will formulate those axioms and the relation. And then I will, at the very end, so I will show one example how we can solve these form factors, octagon, in the PP wave limit of this ADS-CFT correspondence. And then I will also comment how to take into account these virtual particles you learned already in the previous talk, and then how to deal with these singularities in this particular case. So I will sum up this octagon in this case, and I will conclude. So that's the plan. So eventually we are interested in this process in which we have this big string, some multi-particle excitation, and then it splits into two smaller finite-sized strings, and they also have some particles. So I'm interested in this amplitude. So I will first decompactify to have the crossing symmetry. So I cut here, and I open it, and I open further. So this is the geometry in which I'm calculating form factors. And then, first thing you should see that here this small string is emitted. So this means if I just take one particle, and then I'm trying to do a crossing, so move around this emitted small string, what I will see that moving here below and and above is not quite the same. There is a missing volume. So this missing volume will introduce some phase in the form factor axioms. So it's like a form factor of a non-local operator, because something happened in the space-time if you go around. So what happens, so some non-locality is introduced. So whenever a particle crosses this non-locality, it will fill the missing space-time. And then what is the translational phase of this missing space-time is this e to the IPL. So whenever I cross a line like this, I should introduce this factor. So the modification of the previous form factor axiom for this situation is the following. So this is the form factor, which is denoted by NL here. L refers to this finite size string. So periodicity will be replaced with a similar equation, just with this exponential phase factor, transmission factor here. And then if you exchange two particles, you should pick up the S matrix. So these are the new axioms. What about the singularity? So you have these kinematical singularity axioms, and then similarly in the second term, when you go around this particle emission, you will have this phase vector. So these are the axioms, and we are supposed to solve these axioms. But of course, somehow this axiom doesn't really know what particle content is emitted in the small string. So you should find the right solution of these form factors. And then for this, we need to go to finite volume a bit. So just recall that if you go to finite volume, then the finite volume form factors, okay, let's go. So the finite volume form factors and infinite volume form factors are, for large volume, basically the same. So in order to find the right solution, the good tactic is that you take this string theory vertex and then you decompactify it in two different ways. In the first case, you send this L2 and L3 volume to infinity, and you get an amplitude. Okay, it doesn't know about the particle content in L1, but you can send also this guy, this L1 and L3 to infinity, and then in these form factor axioms, you will know the particle content on this small string will appear. So then you can calculate also this, find the solution of the form factor axiom, and then you can demand that in large volume these two things agree, and this should select the right solution. So that's the tactic to solve this equation, but actually these equations are very complicated, and even the usual form factor axioms in which you wouldn't have this phase. So if L is 0, for example, or this red guy is not there, that's the usual form factor axioms, and then it's so complicated, this form factor equation in the ADS case, so we couldn't find any solution yet. So in order to find a slightly better situation, we will decompactify both strings, both outgoing strings. So what we are doing now, we are sending L2 to infinity, L1 to infinity, also L3 to infinity. So it's like cutting twice. We cut here, and also we cut here. So the resulting topology is something like this saddle. What happened actually that string 3 is split into two parts. And the nice way to depict this situation is in terms of this octagon. So observe that this, for example, string 3 is here, it's here. And then if I say would like to make a crossing from string 2 being here, so if I would like to cross from string 2 to string 3, then I can do, it's like this. But then I can move here and then cross back to string 1. So crossing goes like from here to here, and then 3 to 1. And then from 1, I can go to 3 prime. So I'm here. And then going on the other side, I can come back here. So I have this octagon amplitude, and I would like to formulate now equations for this octagon amplitude. So let's put particles, say, in string 2 in this octagon. And then, of course, if you exchange two particles, then you pick up the S matrix. This is one of the axioms. And then we have the just explained periodicity property, which is now not 2i pi than it was in the case of the form factors, but it's 4i pi. So if I take one particle and start to cross and cross and cross and cross back, then it should appear on the other side. So this is also a form factor equation. And then it's complete. The only thing you have to tell, again, the singularity. And the singularity, it's very simple compared to the previous case. And it tells you that if you have, say, one particle here on string 2, here, and then the same particle in string 3, same momentum, then there is a pole in the octagon amplitude, and the residue is just, you remove this pair of particles, and the residue is proportional to the octagon, which contains two particles less. So this is even nicer than we had in the form factor case. It doesn't even contain the product of S matrices. So these are the octagon axioms, and it would be nice to solve these axioms too. So what is the relation of this approach to the hexagon approach? So going back to this original picture, actually you can cut one more. If you cut one more, then this pair of bands will be split into two hexagonal things, like 1, 2, 3, and then there are also prime versions. So in the octagon, this means that you are cutting this octagon half in the middle. And then again, you can formulate axioms for one single hexagon. So what are the axioms? Obviously, if you change two particles, you pick up the S matrix. So these are the same. And then now the crossing symmetry is that you just cross with 3i pi, not 4i pi as before, or 2i pi as in the relativistic case. So it's if you cross once, twice, and the third times, you appear on the other side. So these are the hexagon axioms. And the singularity structure is that if, similarly like the octagon, if one guy in string 2 appears like exactly the same momentum like another guy in string 3, you have a pole, and the residue of the pole is a hexagon which contains two particles less, these two particles less. These are very beautiful axioms, and what is nice about that Benjamin, Shota, and Pedro actually could solve it. That's extremely beautiful, and the solution contains this SU2/2S matrix of Niklas, additionally the dressing phase and some prefactor. You have seen already this solution in the previous talk. So that's the complete solution. So what is, now let me recall what is the status of these three approaches. So first of all, we would like to calculate this finite size problem, when each string is finite size. And then what we did first, we cut on one side. And we got these form factors of this non-local operator insertion. Then we cut twice, and we got these form factors of the octagon. But we could also cut 3 times, and we got 2 hexagons, and then this is the picture, and then we could manage to solve, community-wise, this hexagon. The question, how can we move back? How can we sew back a cut? And that is a prescription, actually, is the following. So let's assume you would like to calculate the octagon from 2 hexagons. So you would like to glue back here, sew back. So what you do, at leading order, you just, that's a 3-particle state, you just take the product of these 2 hexagons, actually distributing all possible ways of these 3 particles. But the leading order correction comes from a pair of virtual particles. So you introduce one virtual particle in one hexagon and the other pair on the other hexagon. And then you calculate these 2 hexagons. And then with some measure, you integrate for all possible particles with some mirror momentum. And also, if there is a distance between these 2 parts, then you have this mirror particle propagation here. So now the prescription is something like you take one pair of particles, two pair, and so on, and you sum up all possible pairs of particles. If you make this summation, then you should get the octagon. So hexagon is nice because it's already solved, but in order to get the octagon, you have to make this infinite summation. Let's assume you already solved the octagon. Then again, you have to solve one more again, sum up all this infinite number of intermediate particle states. Then you would get this non-local form factor, non-local operator insertion form factor. And then here again, so this is more difficult to calculate, but it already sums up infinitely many terms. So that's why it's nice to have this equation also for these guys. And eventually you have to glue back also these two sides, again introduce infinitely many mirror particle states, sum them up, and then you will get the final result. So let's see how this whole program works for the PP wave limit of ADS5 process 5. So we start with the first situation when we cut only one. So this is the non-local operator form factors. And then I will assume I will have just two particles in this string free. Here I have shown four, but let's assume we have two. So in this limit, actually the PP wave limit, the scattering matrix is just 1. So you have to solve this form factor equations with S equals 1. So if you take two particles and if you exchange them, then you would pick up the S matrix, but it's 1, so it's symmetric in theta 1 and theta 2. And we had this non-locality. So if we take this particle and move around, we pick up this e to the minus IPL phase. So this is the second equation which we should satisfy. And additionally, we have the kinematical singularity equation. So if these two thetas are differ just by I pi, then we should have a singularity, and the residue is 1 minus e to the IPL. So we would like to solve these equations. First, we actually solve the first two equations. So it should be symmetric, first of all. So it's a symmetric expression. And then we should solve this monodromy. So to solve the monodromy equation, you just put a e to the minus theta 1 times this p1 L over 2 pi. So whenever you shift theta 1 with 2i pi, you will exactly pick up this phase. So this is a nice solution, but still you have to satisfy this kinematical singularity. So you put a symmetric factor like some function of theta 1 and theta 2, the same function, and then you will see what the kinematical singularity equation will tell you about this product. And you got this functional relation. And then if you investigate a bit this functional relation, you will see that there are many zeros on the real line, and then there are also zeros shifted by I pi. So the only thing you have to do, you have these lots of zeros, and you have to decide whether you put the zero into the n theta or n theta plus I pi. And then physics tells you actually that all the zeros should be on the real line. So one possible way of writing this n then, so you put the same thing, this guy, it will have already the right zeros, and then you remove those zeros which are at I pi. And this gamma is basically, it's a product form which removes the unwanted zeros, then it makes it convergent, and then it moves back the asymptotics into the right form. So it was sort of easy to calculate this form factor, this non-local operator form factor in this case. And then you can compare actually results from string field theory, because in string field theory they already calculated this quantity. They calculated this quantity for finite L3, L2, and L1. But you can take the decompactification limit in which you send L2 and L3 to infinity, and still the formulas are very, very heavy, involved, but you will find exactly the same solution. We found it here in a very easy way. So it's a nice way of solving this problem. But let's see how we could obtain the same thing from the octagon. So what we do now, we take this situation with two cuts, we take the octagon, and then you remember this octagon equation. Let me specify for the two particle states in string 3. So S matrix is 1, so if you exchange, you have the same function, and this function should be like 4i pi periodic. So the solution to this equation, and it should have this kinematical singularity. You remember that whenever they differ by I pi, then the residuum is just 1. So this very, very simple solution is written here. So how can we get this very complicated results from this simple solution? Of course, we have to sum up this contribution of mirror particle states. So first, in order to do it, you need the multi-particle solution. So you can recursively now calculate the multi-particle solutions. And since this is a free theory, Wick theorem applies. And then all multi-particle is just the product of two particle terms. So you have this two particle, and then immediately you know the 4 particle, 6, and so on particle. So let's try now to sum up the virtual particles in the octagon. So you have an octagon, and then let's put just two particles here. And then I would like to make a gluing procedure here down between these two by including one pair of mirror particles, 2, 3, and so on. So let's analyze. So first term is just this leading order. Then this is the contribution of the first Lucher correction, the first wrapping or correction, or the correction of virtual particle states. And then you will immediately realize that because these two guys differ by I pi, there is a pole. So this is the pole you already heard of. You should be careful. But here it's very clear because this pole appears just a disconnected piece. So in order to get rid of the pole in this particular free case, you can just say, let's consider in all these cases just the connected piece. When you integrate it, it doesn't have a disconnected piece. Okay? So you put just the connected one. So you neglect one of them, which is disconnected, this one, and then calculate the other two. And then you do the calculation with this small size of the cylinder as distance putting here. And then what you will find is exactly the same like this other contribution what we calculated in the non-local operator form factor if you expand for large L. So this solution actually contains all Lucher or wrapping correction in the small string. And we just calculated from the octagon the leading correction, the leading wrapping correction. And then you can go to next order, and then you can do the calculation. And actually you will realize that there is no clear prescription which gives rise to the same result, but at each order of the calculation you can choose a numerical weight which gives exactly this result. So I'm telling you that summing up the octagons, the connected part of the octagons in a clever way, you can reproduce the form factor of the non-local operator insertion. So let me conclude. Let me see. Yeah. So the ultimate goal is to calculate this 3-point function with finite sizes, or the string field theory vertex, when a multi-particle state evolves into two other multi-particle states. And then I suggested like 3 procedures depending on the number of cuts. And then the most difficult procedure would be just cut once, and then you got this non-local form factor equations for this non-local operator insertion. But it's very difficult to solve. But if you could solve, this already contains all wrapping correction in the small string. Alternatively, you could make 2 cuts. Then you have these octagon axioms. So these octagon axioms are simpler. It doesn't depend on the finite size string. Kinematical singularity doesn't depend on the scattering matrix. So it should be easier to solve. And then here you have to do just two gluing procedure to get back the result what we needed. Or alternatively, you go to the hexagon approach in which you cut free. What is nice that we know already the hexagons, but then we have to figure out how to glue back the hexagons in the general case, not the PP wave case, which is easy to see, to get this free-point function or the string field theory vertex. So let me stop here. Thank you very much.
Strictly speaking, your axioms and the string field theory only computes the extreme three-point functions. So your method works for extreme three-point functions because you take the outgoing vacuum to be z bar, so the length have to be the same.
No, I mean R charge always should be conserved. It's not extremal, no?
Yes, but in your method it works for extreme case, also the string field theory. But the BKV works for non-extreme case. So my question is, can you generalize your axioms so that you can work for the case where one of the outgoing vacuum is rotated, like in the BKV case, and still formulate axioms for the octagon and the local operator? In this way, maybe it makes more sense to compare.
Yeah. Now, most probably you should represent this outgoing state over a different vacuum as a multi-particle state over this vacuum, what we are using. And then you should calculate all these multi-particle amplitudes, and you should sum them up and then get this result. I can't see how to generalize when you choose a different light cone gauge on the outgoing strings.
Let's see, another question. I think in the old days when people were studying the degree of string theory, I think there are two attitudes towards string vertex. And some people are trying to make connection with the three-point function, but some people are trying to make connection with the matrix elements of non-planar dilatation operator. Have we ever tried to kind of compare string theory vertex you obtained with the non-planar dilatation operator?
No, we didn't. No. But definitely it should contain the 1 over n corrections, because this is the mixing matrix. If in the leading 1 over n correction comes from the mixing between the double trace and single trace operators, and we are sort of calculating exactly this mixing matrix element.
Yes, if you want to go beyond PV wave, the main obstruction is, from what I understood, there seems to be two obstructions. One is this pole that you have to remove. You remove just by looking at the domestic part.
Yes.
And then also you have to add some numerical weights. That's a part in your resolution.
Yes.
So do you have any idea of how to generalize that second part, provided the first one gets rid of the pole?
No, unfortunately not. I cannot even see any guiding principle in this case, except the one that I would like to get back the result I know from solving this non-local operator form factor axioms, which could give the same result. I know that if I would like to calculate a finite volume form factor, 1-point function, then there is a clear guiding principle that you also make so you calculate the 1-point function on the cylinder, and then in the cylinder you also make the other direction finite, so you do the calculation of the torus, and then you introduce this, say, a discretization of this integral for the multi-particle state. Then if you divide by the empty cylinder, I should say, then it normalizes everything. And that's very clear picture, but we don't have such a clear picture here, unfortunately. Yeah.
Other questions? I see one.
Yeah. But calculate what?
You go to the weak coupling and try to find some experimental results. Then somehow you should know the solution.
Of the form factor equations. So you would like to decide which solution to take. That's one possibility. Actually, we checked these form factor axioms for the non-local operator expansion in the weak coupling limit for existing solutions, and we could always see the appearance of this e to the IPL times the product of S matrices. So it's valid also for the 3-point function, these axioms.
Okay, let's thank Dolly for this very informative talk.